Hi and welcome to the video lecture series on wear modeling and simulations in the course M7033T Scientific Computing with applications in tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. This is the fourth and last part of the video lecture and it's devoted to the wear simulation. As you probably figured out by now, the wear simulation in this course will be based on ARCHARD'S law. And in 2D we will also have this centered element type of pressure discretization, and we will assume that wear occurs at these small areas delta A, I, J, as we have magnified here in the middle of the picture. So this means that the element-wise property delta Vij can be expressed in terms of the wear rate K and the sliding distance delta S and the load Vij, which the element is subjected to. Now, if we have the center element type of discretization of the pressure, then we know that Vij is just P. We assume P is constant over that area, delta A, and we obtain Vig as P times delta A. In order to calculate the wear depth, we need the pressure distribution. And the pressure distribution we may obtain, for example, by means of the enhanced contact mechanics solver that includes the plastic deformation that we learned about in the contact mechanics part of the course. And here we have the solution procedure described and refer to section 4.8 in the course compendium for more details on this again. Then a flow chart of the application of ARCHARD'S equation would be starting with an initial surface topography for each the upper and lower surface and their relative positions, and then we run the enhanced contact mechanics solver to compute the pressure and the plastic deformation. And in the compendium this is in figure 4.14. Then we compute the wear depth using the equation we have on the right here, ARCHARD'S wear equation in terms of wear depth. And then we remove material from the substrate of the softer surface due to both the wear rate, due to the wear rate type of wear and ARCHARD type of wear and the plastic deformation. And then we update the system by moving the surfaces relative to each other. So one time increment result in one length increment or change in length like this. Okay, and therefore we end up precisely as what we had before here. If we do this for a smooth ball versus a rough, nominally flat, hard surface that we revolve in this manner periodically, and also we can have as below rough ball against a smooth flat, and then on the left we see the rough ball as it generates a deeper and deeper groove in the flat surface, and on the right, on the bottom right, we see how this wear depth is actually increasing with the passages. So we see, like if we start from, let's see, okay, it continues, let's see when it ends. Now it starts again, so we move, and then we move it over the border, comes in from the other side, and we continue to do that a few revolutions, and therefore we obtain finally a quite uniform wear track, as we can see here. We can have a look through a smooth ball on the flat and see what happens when this rough abrasive flat actually wears the smooth spherically shaped surface. It's seen here, of course, on the left, and then if we, after a while, we stop, we can observe the wear track on the ball, which we see here. We can also quantify the wear volume, and at that certain time step, or at the when we have considered to stop this simulation, we can also find the detailed information about the pressure, as down here. It is very important to consider time discretization correctly, and you will elaborate on this in your assignment. And here you have an example of what may happen. So we have three different time steps relative to the spatial discretization, the mesh size in X and Y direction, which can be assumed to be the same here, or they were assumed to be the same. And then we can see on the top three figures that there's quite big difference between the pressure, because that's the pressure which is shown in those. So the evolution of the pressure is dramatically different in these three figures. So for these three time steps, not such a big difference between second and third. So going from delta t equal delta x to halving that time step doesn't make a huge difference, but halving it in the first place from 2 delta x to 1 delta x is making a huge difference. Now looking at the wear, at the worn surface, so we can see a profile of the worn surface, of the wearing surface I should say, because it's an evolution here. We see that it's not so big difference, and this is actually also seen in the 3D visualization below, which shows you the same thing. So the see-through surface is the original surface, and then you get a worn surface shown in the three examples, and it looks seemingly the same. And if we were about to quantify the wear volume, it would definitely be quite equal, at least if we let it move for some time, like stop it here and quantify the wear volume. It would be pretty much the same for all three cases, although the pressure distribution would differ dramatically. So what about comparing our numerically simulated result to measurements? What we see here is a figure taken from the paper with reference below here, where we measured wear using AFM. And so this is before and after surface measurements before and after wear in a ring-on-ring test type configuration, and with one of the rings were rough and one was significantly smoother than the other one, and then we had these results. And what you see actually is the wear depth. So it's an inverted map of the wear of the surface. So it's where the surface has worn the most, where you see these peaks, these protrusions, and you can see that they are on sort of diamond-like edges, both of these protrusions or areas of protrusions, and it's because that we have nano-idented these surfaces, not only to test the hardness of them, but also to be able to relocate the surface after wear to measure it at the same time, to actually quantify the wear like we have done here. Now, by a little bit of reverse engineering, finding the wear rate coefficient in the ARCHARD wear equation, we obtained this result with numerical simulation, as we have described it previously here. So the same type of methodology led to this result, and I think it's pretty fascinating how similar they are. Of course, it's a huge difference in the wear sort of observed everywhere else, but on the ridges of these diamond-shaped pits. But that is also because of measurement errors. So we cannot be so certain that we actually have that type of wear on the sides of these pits. But yeah, it's likely that there is also wear there because of the elastic deformation, plastic deformation, and the wear of the abrasive type. Pretty similar results. Fascinating. The reasons for wear simulation are many, and for example, one reason could be if we observe that the machine element experiments unexpected amount of wear, or wear in an unexpected location where we perhaps have difficulties to see where the problem comes from. We can run a simulation and perhaps get a little bit more insight into this. We can optimize tolerances in production. Maybe the tooling, maybe the substrate that we form, shape into the piece of the production piece or whatever. It could be already in design stage to reduce some expensive testing, because you know, of course, the dearer the test becomes, when we have as close to the reality as possible to test, full-scale test. And we can also make better materials and perhaps more clever lubricant selection during a design stage if we have a little bit more insight into the wear mechanism. We can also run wear simulation if there is a high risk of boundary or mixed lubrication, because then we know the surfaces will wear, and we can definitely be helped of understanding a little bit more on how much it will wear and so on. To carry out the wear modeling and simulation, we propose following modeling strategy here. So it starts by identifying material parameters, so in terms of elastic moduli of both the contacting bodies, Poisson ratios, hardnesses, so we know which one is the softer one and how soft it is. And then we identify the contact geometry, we parameterize it in some sense, we discretize it, of course. We then implement some kind of model for the contact load and the sliding speed. It depends on what system we are simulating, of course. And we estimate the time resolution required to capture the wear correctly. As you saw, it was crucial to pick small enough time step, but it's also crucial to pick as large enough time step so that we actually can perform the wear simulation in reasonable time. We need also to acquire roughness data, so the microscale topography of the surface is very important, of course, and we need to set up some kind of interpolation routine so we can map this roughness data to the surfaces at an arbitrary step in time. And then we should run this wear simulation iteratively by using the suggested solution procedure as we have here on the right. During this part of the course you have an assignment to do, assignment 4, and it's actually a numerical pin on disc experiment, as you can see it, with a ball-shaped pin end and a nominally flat disc. And I have a simulation here on the right to show this. Notice the scale, so the lateral scale of this one is in decimeters, and then the height scale is in micrometer in order to show the wear, of course, and therefore the spherically shaped pin gets a quite sharp radius of curvature. So you should consider now in this assignment the roughness, and it should be possible to place roughness on both the pin and the disc, or run them smooth, both of them being smooth. You should study the sensitivity with respect to the choice of the time step delta t, and how that influenced the evolution of the contact pressure and the wear. And you should also study the influence of plastic deformation, or in terms then of the plastic yield pressure, which will be an input for your contact mechanics solver, and how that influenced the evolution of the contact pressure and the wear. So that was it. The lecture on wear modeling and simulation is finished by this.